Hello, everyone. I'm very glad to attend this conference and give a presentation today. My name is Lu Chang, a postdoctor from Dr. Lin Riyi's group from College of New Energy, China University of Petroleum, East China. The topic I will give today is study on supported transition metal catalyst for desulfurization and viscosity reduction of heavy oil. Firstly, I'll give a brief introduction. Secondly is the technical rules. Then follows with catalyst preparation and characterization, and the catalytic viscosity reduction and desulfurization experiments. And in the end is the conclusions and the prospection. As we all know, heavy oil production plays a very important role in worldwide hydrocarbon development. The proven reserves of heavy oil in the world are about 815 billion tons, accounting for about 70% of the remaining reserves of global oil. And China is the fourth largest producer of heavy oil in the world, with reserves of about 4 billion tons, accounting for about 20% of the remaining oil reserves in China. However, heavy oil has very high viscosity, which leads to poor fluidity. Thus, it's very difficult to exploitation, gathering, and transportation. At present, the development method of heavy oil mainly include 4 types. The first one is conventional heating technology, like SACD, FAST, and so on. And also, we can use physical method, microbial method, or chemical method to reduce the heavy oil viscosity. Among them, the in situ catalytic upgrading of heavy oil technology, which based on the hydrothermal cracking reaction of heavy oil, has vast potential for further development because it can irreversibly reduce the viscosity of heavy oil. At present, China has a large amount of heavy oil production. The thermal recovery of heavy oil accounting for about 10% of total crude oil production. However, its energy consumption is relatively high. Taking Xinjiang oil field as an example, heavy oil production accounts for 1/3 of the entire oil production, while the energy consumption accounts for 2/3. Thus, in situ catalytic upgrading method is a promising method to recover the heavy oil, which can lower the reaction temperature and reduce the energy consumption by reducing the cracking reaction activation energy. However, this method still have some deficiencies. The first one is that the performance of the catalyst is not up to the expectation. And the second one is that the reaction temperature is still relatively high, and the application temperature range is relatively narrow. Thus, we would like to develop a kind of catalyst which have good catalytic performance on heavy oil viscosity reduction at a relatively low reaction temperature range. And to achieve this goal, we would like to use the solid acid catalyst as a target catalyst, because these kind of catalysts have relatively good performance and its modification is relatively flexible and easy. 2 transition metal components A and B are selected as active ingredients, and the molecule sieve C is used as a carrier, which can improve the overall structure stability of the catalyst. After preparation and characterization of the catalyst, we will test its desulfurization and viscosity reduction performance from 4 aspects as listed here. And here comes with the catalyst preparation and the characterization part. Firstly, the nano-supported catalyst with different loadings were designed and prepared. Then we characterize it. We use XPS to detect the valence state of the transition metals and verify the loadings of the active components. And the XRD method tests the composition of the catalyst by detecting the diffraction peaks of the carrier and active components. And the N2 sorption isotherm indicates that the catalyst has a mesoporous structure. The BT data of the carrier and the catalyst are shown in this table. The largest specific surface area can promote the contact between the active components and the reactants. And the large pore size can permit the free entry and exist of heavy oil macromolecules. And these 3 TEM scanning pictures shows the critical phases of the active components. We also did Ammonia Tpd Test. The graph shows that the surface of the carrier, which is line A, has many weak acid sites. And after the active components are loaded, the exit area and the number of strong acid site increases in the high temperature zone, which is shown here. And the second graph is a TGA graph, which shows a good thermal stability of our catalyst. And after all the characterizations and making sure the prepared catalysts are in line with our expectation, we would like to test the performance of catalyst on heavy oil viscosity reduction and the desulfurization. The experimental devices are shown in these pictures, mainly including high temperature and high pressure reactor and the rotary viscometer. And the experiment follows the typical procedure, and the experimental condition is shown here. Due to the time issue, I will not give a detailed description of it today. However, we have 7 groups of oil samples with different additives are used in the experiment to investigate different influence factors on catalytic viscous reduction and desulfurization. Group A works as a reference experiment. Only oil and water are added, and on this basis, hydrogen donor, the titling is added to group B, and the hydrogen donor and the molecular sieve C is added to group C. And in group D, E, F, and G, except the hydrogen donor and the molecular sieve C, catalysts with different loadings are added to the oil sample for the catalyzer reaction. And the catalyst usually in group D and E contains dual active components with different amounts. And the catalyst in group F and G only contain one kind of active component. And we use the heavy oil from Qingdao oil production plant as the oil sample. And the physical properties of the oil sample are tested firstly, including the viscosity, SARA, and the element analysis of the oil sample. We can conclude that the oil sample is a non-Newtonian fluid with high content of heavy resin and asphaltene. And the degree of unsaturation of the carbon is very high. Then we test the catalyst desulfurization and the viscosity reduction performance from 4 aspects. The first one is the influence of the hydrogen donor. Petroleum is added as a hydrogen donor here. The first graph shows the viscosity of the oil sample at 50 degrees centigrade after reaction at different temperature. Group A has no hydrogen donor added, while the group B has hydrogen donor added. It shows that the addition of a hydrogen donor inhibits the rebounds of the viscosity of the oil sample after the reaction. That's because the combination of hydrogen atoms in the hydrogen donor with the reactive free radical inhibits the polymerization reaction of the hydrocarbons. And the second graph shows the influence of hydrogen donor or heavy oil desulfurization. And the sulfur content in the oil sample after the reaction of group B decreases significantly. And the ARA table shows that the aromatic contents increased, which proves that the addition of hydrogen donors promotes the hydrothermal cracking reaction and helps the upgrading of heavy oil. And we also did the Ftir test, and the spectrum of heavy oil group A and group B oil samples are shown in the left-hand side graph. And there are 4 main absorption peaks in the oil sample, which represents the absorption vibration peak and the stretching vibration peak of the methyl group and the methylene group, respectively. The peak intensities are shown in the following table. And it can be found that the absorption peak intensity of methyl and methylene groups increases, which means their contents increases after addition of hydrogen donor. And the picture on the right-hand side is the element analysis of oil samples. And it can be found that the hydrogen-carbon ratio increases after the hydrogen donor is added. Next, we will investigate the effect of different types of catalysts with different loadings on the viscosity reduction. And the oil sample is prepared on the basis of the presence of hydrogen donor, which is group B. All the viscosity reduction experiments were conducted at the temperature of 280 degrees centigrade. The first figure shows the viscosity reduction rate of the oil sample catalyzed by different catalysts. And group D and E have the best viscosity reduction performance. And the second figure shows the desulfurization rate of different catalysts. Group D, E, and F has relatively good desulfurization performance. And this figure shows the quantity change of SARA of the oil sample. We can see the group D, E, and G has relatively good coke production inhibition performance. Because the contents of asphaltene, which is the yellow bar, is greatly reduced. And from the element analysis, we can see that the group D and E has the highest hydrocarbon and hydrogen and carbon ratio, which indicates the good heavy oil upgrading performance. Then the role of carriers A, active components A and B, in the viscosity reduction process was analyzed. The FTIR results of our example shows that the carrier C in group C can promote the methyl production due to its strong surface acidity and better pore structure. An active component A can promote the production of methyl and methylene. And the component B also has some certain effects on viscosity reduction, but not the main factor. However, in the previous slide, we can say that the main function of component B is to reduce the asphaltene contents because it can inhibit the production of coke. And the previous result shows that group D and E have the best performance. And consider the economic issue, group D was selected to study the effect of reaction temperature. And group B is conducted as the reference experiment. The first figure shows the viscosity reduction rate of the oil examples of group B and group D. After the reaction at different temperatures, the viscosity reduction rate increases from about 10% to nearly 30% at 160 degrees, and reaches more than 80% at 320 degrees. And the second figure shows the sulfur content of the oil example after reaction at different temperature. It can be found that the desulfurization effect increases with the increase of temperature. And these two figures shows the contents of SARA of group B and group D. And it can be found that the heavy oil components of oil example decreases significantly with the increase of temperature and the action of catalyst. And the last figure shows the hydrogen-carbon ratio in the oil example after the reaction. And it shows the catalyst in group D can enhance the upgrading effect, and the effect is proportional to the temperature. Finally, we investigate the influence of the amount of catalyst on the viscosity reduction. Group D was taken as the research object, and the experiments were conducted at 280 degrees centigrade. The result shows that with the increase of the catalyst addition, the viscosity reduction rate gradually increased, and the sulfur contents in the oil example decreased. And the heavy component decreased, and the light component increased in the oil example. And the viscosity reduction effect tended to be stable when the addition amount is about 1 weight percentage. And through about research, we can draw the following conclusions. The first one is a supported nanocatalyst with metal oxides A and B as active components and the molecular sieve C as a carrier was designed. The second is the hydrogen donor can effectively reduce the viscosity response of heavy oil after the reaction. And we also found the dual active components have a stronger viscosity reducing effect than single active components. And the catalyst is effectively at low temperature and stable at high temperature, and the viscosity reduction rate reaches nearly 30% at a low temperature of 160 degrees. And the viscosity reduction rate reaches over 80% at a high temperature of 320 degrees. And in the future, we also would like to further promote the low temperature activity of the catalyst while ensuring the stability of the catalyst under high temperature condition. And for the in situ upgrading technology of heavy oil, we can also take the complex pore environment of the formation as a consideration, and investigate the migration and the transfer law of the catalyst. That's all my presentation today. Thanks for your attention.